how to attack machine learning training environments. Bruce, welcome.
Thank you very much. Yeah, thanks for coming to my talk right after lunch. So really appreciate you coming here. We're going to talk about attacking ML training infrastructure today. I'm Brett Hawkins, and I am with IBM X-Force Red. Before I get started, I want to put these QR codes up here. Last week, I released a blog post on this research with full details that I'll be covering today, as well as I released updates to my MLOps attack toolkit last week as well in support of this research, so I'll just leave this up here in a second. I'll be sharing the slides this week. I have the last slide also has these QR codes as well. All right, agenda for today. So we're going to start off with some introductory and background items. That'll take about 15 minutes, and then we'll get into actually attacking these ML training environments. There's a lot of demos in this, about 20 minutes of demos here, so it's going to be a very demo-heavy presentation. After we cover attacking these ML training environments, I'm going to switch gears and talk about, from the defensive side, how you protect these ML training environments. And then should have about 5 to 10 minutes for Q&A at the end. So an introduction. So I'm Brett. I'm one of the team leads on the adversary services team at IBM X-Force Red. Our team does long-term red team engagements for clients, typically like 2 months, targeting some type of objectives, trying to evade security controls and security teams. I've spoken at a number of conferences listed there. I've also got a number of open source tools that I've authored. If you're interested in any of my public security research, definitely check out that link there. I've got all my white papers, presentations, blog posts, tools, etc. So what was some motivation around this research? Why research attacking ML training environments? We see, at IBM, we're seeing more organizations developing private models using both private and public data sets and integrating them into products and services that they sell to business and consumers. And with these ML training environments that are used to train these models, there's currently a lack of research on attacking and defending these environments. Also, there's a lack of tooling to simulate attacks and build detections against the platforms that are used within these ML training environments. And because of this, now we're also seeing threat actors starting to target these environments. And from a threat actor perspective, why would they be motivated to attack these environments? So first off, the ML training infrastructure and the platforms that are used within them, it's a significantly expanded attack surface for threat actors. A lot of times they're going to have direct access or sit adjacent to enterprise data lakes or any type of crown jewel type of data. So compromising these systems could allow you to gain and expand privilege escalation, steal sensitive data, things like that. And currently, security teams, they lack detections or threat hunting playbooks for these new data science tools and platforms. And a lot of times these environments themselves are very poorly secured. And so because of that, it makes them a very attractive target for a threat actor. So it's very important that we understand the motivation for these attackers in order to protect these systems. So I've got some listed there. Some things you're going to see in this talk. Attackers, they want to steal models. They want to backdoor models, potentially use their access to laterally move around, maybe even conduct a ransomware attack by stealing training data or models and say, hey, if you don't pay me, I'm going to release this. So lots of different motivations here from a threat actor perspective. Now, as far as what you're going to take away, whether you're on offense or defense, you're going to get something out of this talk. From an offensive standpoint, you're going to learn how to steal models from model registries. You're also going to learn how to poison models within training environments. And another thing on the offensive side, you're going to learn how to get code execution via attacks on ML training infrastructure. And from the defensive side, you're going to see how to defend key components of ML training infrastructure. As far as what's new in this research, so I've got some advanced attacks against ML training environments, things like model poisoning, notebook environment attacks. I also released, as I mentioned, some updates to my MLOKit tool as part of this research, which includes the support of new platforms, MLOps platforms, and new modules and attacks. And then lastly, I created some detection rules, or really you can use as threat hunting rules, against Azure ML and SageMaker as part of this research. Now, before I really get started here, so my perspective on this, I've been doing offensive cybersecurity for almost 10 years now for a number of different organizations. So that's really the experience and the perspective that I bring to this research. I'm definitely not a data scientist. I'm definitely not an ML engineer. What they do is pure magic to me. Yeah, I'm definitely not any of those things, but this just kind of want to make it clear, like, this is the perspective that I bring. All right, now we're going to go over some background items. So as far as prior work, Chris Thompson and myself, we released some research at ShmooCon in Washington, D.C. in January that was specifically around stealing models and training data from Azure ML, Vertex AI, and Big ML, which are a few different platforms used within these training environments. I've expanded that research since then, with targeting different platforms and different types of attacks in this research. Also want to call out Or Azarzar. Or released a blog post in 2021 around abusing something called SageMaker Notebook Instance Lifecycle Configuration Files. So I kind of took that research and automated it as one piece of this research that you'll see. So ML technologies, all kinds of industries now, whether you're automotive, healthcare, financial services, are using ML technologies, and those are in the products or services that they sell to consumers, other businesses. Some example of ML technologies, things like driver assistance systems, autonomous vehicles in the healthcare industry, using ML technologies for drug discovery and development or medical imaging analysis. So these are things that I think you can kind of understand are in the public now and are being used. In order for those to be used, what has to happen? Well, behind these ML technologies is a model. And you can think of the model as just kind of like the brains behind the operation. And to develop that model, the model development and deployment goes through what's called an MLOps lifecycle, or MLOps process. So you have the MLOps process that develops and deploys a model, and that model is used by these ML technologies. And we would talk about MLOps. So MLOps is machine learning operations. It's really at the intersection of DevOps, machine learning, and data engineering. Oops, did it? There it is. Really the goal here is to provide a consistent and automated process to get a model into production so it can be used by ML technologies. And within this process, there's a number of different platforms that can be used to develop and deploy a model. There's both commercial platforms and open source platforms. On the commercial side, you're going to see a number of different platforms there. The ones that I covered in this research on the commercial side are Azure ML and Amazon SageMaker. On the open source side, I cover MLflow in this research. Now, what does the MLOps lifecycle look like? So when we have these platforms, what actually happens? Well, first off, you start in the design phase. This is where you're collecting and organizing your source data, and this is really the most important part of the lifecycle because the quality of your model is going to really depend on the quality of the data being input. From there, you have your organized and sanitized data, and that's going to go into the develop build process where you're actually going to train ML models from that phase. After you train the model, you're going to test it, trying to answer the question, is this model doing what it's supposed to? After you've went through and tested your model, then you want to deploy it to production so it can be used by ML technologies. Really common use case is deploying a model as a REST API. And then after that, just like any type of production infrastructure, you're going to monitor it for any quality issues, performance issues, things like that. Now, where the ML training environment fits in is the develop/build phase. So this is going to be the phase of the MLOps lifecycle that we're going to be targeting today. And within that training environment, there are a number of different infrastructure components that are very critical. And so how this works, so you have first off, you have your personnel. These are going to be your ML engineers, your data scientists, even software developers that are maybe wearing multiple hats. They're going to use a notebook environment. Jupyter is a very common one if you've heard of the Jupyter notebook environment. They're going to use this notebook environment to run their ML training code, the actual code that's running the training jobs. Now this code is typically going to be managed in a source code management system. I've got a few listed there. This training code is going to run within cloud compute. You could call these experiments. Training jobs is another way to kind of reference it. And you want cloud compute because you want as much compute as possible. Think like deploying like a cloud compute in SageMaker with some NVIDIA GPUs. That way you can run the training through as many permutations as quickly as possible. The training output, so the output files from this training exercise will then be written to some type of model artifact storage. So I've got a few listed there. Think like S3 storage, Azure Storage Blobs, or Google Cloud Storage. And then from there, what you will do is you'll register your best performing model within what's called a model registry. You can just think of a model and a model registry as just simply like a pointer to a correlating training job and its associated model artifacts. And then to deploy a model to production, like as a REST API, that would be deployed from a model registry. So that just kind of gives an overview of how this infrastructure fits within the ML training environment. So drilling a little bit deeper, so I mentioned these notebook environments. It allows data scientists and other MLOps personnel to run training experiments along with any other tasking they have. And again, that training code typically is going to reside in a source code management system. And there's typically some type of automation set up so that if you make a change in the source code management system for the training code, it reflects in the notebook environment. That screenshot there just shows an example of opening like Azure ML and seeing the notebooks that are available there. An Amazon SageMaker, this is just an example showing I have a notebook environment. You see the repository URL there is pointing to, I have a source code management repo, and the notebook environment is pulling that training code in from a source code management repo, just kind of showing the connectivity there. Cloud compute, again, this is going to be infrastructure that you spin up on demand to perform that ML training. So the Jupyter notebooks will run the ML training code within the cloud compute. So think things like Azure, AWS, or Google Cloud. Then you have the model registry and the model artifact storage. So again, the model registry, it just allows you a single place to track and version models that you want to potentially deploy to production. And this is typically going to contain the best performing models from the training process. And then you have the model artifact storage, and that's going to be the actual output artifacts from each training run, which is going to include things like model weights, which is kind of like the inputs that you're giving to do the training process, which is very valuable, and I'll talk about that in a little bit. The metadata for the model, and also the actual model files themselves. And so what does this look like in MLflow? So I have the bottom left shows I have this model registry, this registered model here. This registered model points to a experiment run, that rumbling ray experiment run. And then that experiment run has correlating model artifacts that point toward S3 storage. So for example, if I have access to MLflow, whenever you configure MLflow, you configure a connection to S3. So if you compromise access to MLflow, you don't need any type of access key or secret key to get to the backend S3 storage, because it's basically MLflow is already connected to the backend storage. So you gain access to MLflow, you can then access any model artifacts that are connected to MLflow. With Amazon SageMaker, again, you have a model registry. That model is going to point to a training job, and then that training job is going to point to the actual model artifacts in some type of artifact storage, in this case, S3. And then the last example here for model registry and artifact storage is Azure ML. So I have this registered model in Azure ML, this salary model, that really just points to a training job, and then that training job points to some type of model artifact storage. Now, something interesting with Azure ML is that they have these things called data stores, Azure ML data stores. And that Azure ML data store, it just references the back-end model artifact storage. So what that means is, if I compromise a data scientist, for example, I can just interact with the data store itself with their credentials. I don't need to have some sort of SaaS key to the actual back-end Azure Blob storage. And so, for example, the data store object in the Azure ML REST API, you're going to see me abusing a little bit later, that has the connection information needed to connect to that back-end Azure Blob storage. All right, so we got some background stuff out of the way. So about 15 minutes of kind of introductory background items, because it's really critical for these next pieces. Now we're going to switch gears and put on our attacker hat and look at actually attacking these different components. So previously I had a diagram that showed the legitimate uses and for the different infrastructure components. Now we're going to think like an attacker here. So these Jupyter Notebook environments, why are these useful from an attacker perspective? Well, these notebooks, really at the end of the day, these notebooks are just source code, right? So think source code secrets, notebook secrets. These notebooks can contain credentials that aren't being properly secured by data scientists or MLOps personnel. And so you could, steal credentials in here, get access to other APIs, other infrastructure. Another thing that you could do is potentially use this information to discover other infrastructure within the environment. Model registry, again, model registry just points to actually the back-end model artifacts, and so the model registry really is just useful from a reconnaissance standpoint as an attacker. So I can see which models I may want to target for model theft or poisoning, because it's going to have the metadata. What is this model? Is it used for some type of employee PII? Is it used for, whatever, right? So if I'm targeting a specific type of data, this is going to assist me in that. The model artifact storage, this is where the goods are. So this is where they're going to be the actual fully trained model, the weights used. It's going to have sensitive data, like that fully trained model is very sensitive, and you're going to see some different use cases in the demos here. But this is probably I would say the most sensitive here is the actual model artifact storage. And then lastly here, the cloud compute. So if you get access to cloud compute, what could you do? Well, these systems that run the training code, they typically have sensitive environment variables, which you could use to laterally move throughout the environment or escalate privileges. Think of maybe some, access keys, secret keys for AWS, or maybe with Azure, you might have some Azure Service Principal credentials. Really, there's, the sky's the limit there. Additionally, I mentioned that the ML training code will be running in the cloud compute. So if you gain access to cloud compute, you could then have access to the ML training code, which obviously could be a very valuable from an attacker perspective. So we've kind of looked at these different components from an attacker perspective. Now I'm just going to give an overview on some of the attacks that I'm going to show here in the demos. First off, model theft. How would an attacker go out about doing model theft? First thing they would do is do reconnaissance of the available models in the model registry, and then they would download the correlating model artifacts from that model. Now you might be asking, well, what's the big deal? What's the impact of stolen model artifacts? Well, there's a number of different things. First off, intellectual property theft. So by stealing those model artifacts, it will enable you to look at the proprietary algorithms, the architecture, the training strategies that are embedded in the model. Model extraction and replication. If I steal a model that is used for, let's say, fraud, classifying fraud or malware analysis, I can then, I can steal that. I can do a couple things. I could replicate that model and try to evade the behaviors within it, or if I am a nation state, I can steal that model and then develop my own model just like that, but reduce the development costs because you've done all the training for me. I just talked about already adversarial attacks and evasion, so if I grab the model artifacts, I know how it works. I can then craft bypasses for it, so think something that does fraud detection, malware classification. If I steal the model and know how you're analyzing things like fraud detection, I can then use that information to get around that system. Backdooring is something you're going to see in the demo, so altering the model to do malicious actions kind of downstream. So we're going to do that in the demos for doing code execution. Some of these, so compromise the system security. Some of these models, they might have embedded secrets or passwords within them. And then lastly, competitive intelligence and strategy analysis. So by having those model artifacts, if I can analyze that model and reveal the business logic that it's using, which again, this could be very sensitive because businesses spend a lot of time and money training these models to do a specific function. So they don't want that information to just be, revealed to an attacker. Model poisoning for code execution, how would this work? So you start off with model reconnaissance, download the model artifacts, modify those model artifacts, and then upload to artifact storage so that when the correlating model in the registry would be deployed to production, we get code execution. And you're going to see this in a little bit. Now, what would the impact be here? So whenever you deploy a model, it deploys to what's called a deployment endpoint. So what would be the big deal? What would be the impact if an attacker gains access to a deployment endpoint via something like this code execution attack? Well, first off, they could just exploit that deployment endpoint for free compute. They could overwhelm it, cause service disruption. With data exposure, intercept, if you're on the deployment endpoint that is, deployed like a REST API, you could do something like intercept the traffic that's going in and out, which could be very sensitive. Model theft, you might be thinking, well, you've already stolen the model and you poisoned it and you uploaded it. What do you mean model theft? Well, sometimes on a deployment endpoint, you can have more than one model deployed. So if I am on a model deployment endpoint, any other models that are being served through there, I would have access to those, which including, if I'm on that deployment endpoint, I could potentially tamper any other models that are deployed on there. And then lastly, so with infrastructure and lateral movement, just like the cloud compute, these deployment endpoints, they might have credentials, whether it's environment variables, things like that, that would allow you to privilege escalate, laterally move around the environment even more. Now, another thing that is that needs to happen to do these code execution attacks with model poisoning, the model files themselves, they need to be a format in which supports automatic code execution. So this diagram here in the correlating blog post, this is from the team at JFrog. They did a really good research presented at Black Hat USA last year. And the formats in the red support code execution automatically, and the ones in green don't. And what I mean by that is, when you deploy a model, if it is one of the formats in the red, upon that model being loaded, it will execute code. So in order to do this type of code execution attack, it needs to be, whenever you're modifying these model artifacts, it needs to be one of those formats. Something that's gained a lot of attention are pickle-based models. It's a very popular model format. There's been a lot of really great research on that format itself and getting code execution. And now you're probably wondering, well, how do I create a malicious model for code execution to upload to this model artifact storage? And there's a few really great tools here. These are, again, really good open source tools for creating those malicious models for actual code execution. Now, the tool I released this year, the MLOps Attack Toolkit, MLOKit, this is another tool you're going to see highlighted in the demos. You can do a number of different attack scenarios with this tool. It is a C# based tool, so you can run it in memory with your favorite C2 framework, or you could run it on your attacker system through a SOX proxy. Lots of options there with it being C#. And what this tool does, it allows you to conduct actions programmatically against the REST APIs that are available with the different platforms used in the ML training environments. It supports authentication with a number of different mechanisms there. I've got 9 different modules for doing things like recon, training theft, model theft, things like that. And I've also got 5 supported platforms. History of this tool, just a little bit. So the initial version was released at SMooCon this year, and then I just updated it last week for Troopers. So new modules, new platforms, and just like any open source tool, bug fixes. All right, so now we're going to get into demos. I got about 20 minutes of demos here, so we'll go ahead and get started. So first off, before these demos, all of them rely on getting some type of credential material. Number of different ones listed here on how you could get some credentials to gain access to these systems. For the open source platforms like MLflow, they, by default, it's unauthenticated access. So some of these platforms, like the open source ones, you might even get access to unauthenticated. So just kind of want to set that stage here that you need some type of credentials to get access to these systems. So 6 different scenarios I'm going to show here. First one I'm going to show is getting access to MLflow and then stealing a model from its model registry. So in this scenario, we have gained initial access to an organization via phishing and escalate our privileges with an Active Directory. With those escalated privileges, there's a number of different Active Directory privilege escalation methods. We've laterally moved to a data scientist workstation, dumped their workstations to get access to Azure ML. And within Azure ML, this data scientist had a Jupyter notebook that had credentials within them for MLflow. So what we're going to actually show in the demo is using these stolen credentials from this Jupyter notebook, from this data scientist, to actually steal the model artifacts from MLflow. So again, we're going to use MLOKit here. First thing we're going to do is run the check module. This just checks to make sure that your credentials are valid to a given platform. Let's go ahead and run this command here. All right, so you can see our credentials are valid, so we're good to go. After we validated access, we need to do that model reconnaissance against the model registry. So to do that, we're going to run the list models module. And this is going to give all those models that are available to us with these credentials. So you can see here we've got access to a few different models here. To actually download a model and its correlating artifacts, you need to copy out the model name here. So we're going to go ahead and copy one of these out. And again, MLflow is going to be connected whenever you spin up the server to whatever backend storage. So I don't need the S3 access key or the secret key. Me just have to get access to the model artifact storage. Me just having access to MLflow is all I need. So the model ID field, we're going to go ahead and put the model name. And then what that's going to simply do is it's going to download all of the model artifacts for that given model. So again, this just kind of shows, the damage you can do with just a model theft attack against MLflow. So you can see some of the files it's grabbing. It's grabbing the actual model pickle file. That's the actual serialized model file itself. And then any, training weights, any type of code, things like that. So for these next few demos, we're going to switch to Amazon SageMaker. For this one, we're going to take advantage of an integration with a source code management repo. So just to set the stage here, again, fished into an organization. We started doing some internal recon on their file shares, like we always do if you're a red teamer, and we've discovered a personal access token to Azure DevOps, which is a source code management system. Now what we're going to do here is we're going to take advantage of the integration, some automation that is commonly set up between a source code management system and then an ML training environment. So think of something like you have your source code management system, you have some DevOps pipelines that whenever you push code changes, it connects to your training environment and then runs that training code. So what we're going to do here is we're going to modify something called an ML project file. An ML project file, you can think of it like a CI/CD config file in DevOps, but these are used within MLflow projects. And so we've got this personal access token. For Azure DevOps, we're going to go ahead and clone the repository that we discovered this ML project file and the training code. Again, training code is typically living in the source code management system. All right, so what we're going to do here is we're going to modify that ML project file. Right now it's configured to run the training Python code. We're going to simply modify this command to run a reverse shell for us, just as a proof of concept. Now, other than modifying this ML project file, you could modify the Python code too, right? You could put your reverse shell in there to be a little more sneaky, but just kind of wanted to show the impact here of gaining write access to a source code management repository that's integrated with ML training process. So we modified the command that the ML training code is going to run our reverse shell. So we're going to go ahead and commit this code to Azure DevOps, where we got some automation in the background that upon a code change, the notebook environment will pull that code in and then run it. Another example may be the data scientist. If there isn't that type of automation set up, data scientists might have their own automation set up to pull code changes or just manually pulling code changes from the source code repos. So you can see here we got this workflow running though. It's running our updated code. And so again, that's going to be running in the SageMaker Cloud Compute. And so on the back end here, we should get that reverse shell from that modified file. Come in here in a second, I promise. And there it is. So again, just to recap, now we're on SageMaker Cloud Compute, and we did this by taking advantage of compromised access to an Azure DevOps repository. This third demo, so I mentioned at the beginning of the talk, or Azarzar released research on abusing these things called lifecycle configurations in SageMaker to get code execution. Or showed doing it in the web interface in AWS, and what I've done is automated this with mlokit. What these lifecycle configuration files are is you can basically have some type of script run before your notebook environment starts or stops, and it runs in a privileged context. So for this attack scenario, we've discovered some AWS security credentials within public GitHub for an organization. And then from there, we're going to use these credentials with mlokit to create a lifecycle configuration to gain access to the SageMaker Cloud Compute it's associated with. And so the stolen credentials here, they're going to need the AWS managed policy for SageMaker of Amazon SageMaker full access, which means the credentials need administrative access to SageMaker. Go out again. All right, sweet. All right, so we've got the credentials. We got these credentials here, so we're going to start off doing some reconnaissance of available notebook instances. So we're going to run the list notebooks module. What this will do is say, hey, are there any SageMaker notebooks that are available to us? And so what you'll do is you'll copy out a notebook name. Again, these notebook instances are tied to a correlating cloud compute. So we want to get access to that correlating cloud compute. So for this, we're going to target this Brett Jupyter notebook. I want it to run this script on my attacker system that I'm going to upload to SageMaker, which is, again, just a simple reverse shell. And so I'm going to go ahead and run this add notebook trigger module. And it's going to do a lot of different things here. So first thing it's going to do, it's going to create that lifecycle configuration. Second thing it's going to do is it's going to stop our target notebook. Because in order to assign a lifecycle configuration to a notebook, it has to be stopped. So after it stops the notebook, it's going to update that notebook instance so that it uses our malicious lifecycle config. And then the last step is to start the notebook. So in this case, we have it configured so that the tool, what it does is whenever the notebook instance starts, it runs your script. So we're starting the notebook, and so our script should run now on that SageMaker Cloud Compute in a privileged context and give us root access to the actual correlating cloud compute. So the notebook starting here should start seeing the shell come in here in a second. And there you go. There's our access to the SageMaker Cloud Compute, again, taking advantage of a feature in SageMaker called lifecycle configurations. Next demo, we're going to show doing model theft from SageMaker. This scenario, we've discovered some AWS security credentials on public GitLab for an organization, one of the Gits. And so from there, we're going to use the credentials to steal a model from the SageMaker model registry. Now for these stolen credentials, it's going to need read-only access to SageMaker and read-only access to S3 storage. So we've got these AWS security credentials. First thing we need to do is do that model reconnaissance. So we're going to list any models in the SageMaker model registry with mlokit here. So we're going to go ahead and run this command. And you see we've got a few different models available to us. To download a model, you need to give the model name for the model and its artifacts you want to download. So what mlokit will do is you give it a model name that you want to download, and it will figure out the correlating artifact storage here and then download those model artifacts. Now, why I mentioned that these stolen credentials need SageMaker and S3 read-only access is because in this case with SageMaker, you do need to have credentials to the actual backend storage. So what I've done here is I've downloaded all the model artifacts from this employee salary model. So you can see here, it figures out the model artifacts location, which is Amazon S3 storage in this case, and then it has downloaded all those to a folder that it created on my system. In this case, this model, it had all the artifacts zipped up here in a tar.gz file, so I'm just going to show extracting these files here. And we're going to continue on from this demo in the next one and actually poisoning this model by modifying the model artifacts. So you can see here, we've got these model artifacts. Just to recap, we've got some stolen AWS security credentials, and that are for both SageMaker read-only access and S3 read-only access. and we've used those with mlokit to steal model artifacts from a model in SageMaker registry. So now we're going to take these, we've got these model artifacts, we're going to modify one of them to actually poison a model for code execution. So for this attack here, in order to be able to do this model poisoning, you're going to need write access to S3 with these stolen credentials, and you're going to need read access to SageMaker. So just, again, piggybacking on that last demo, you can see the model artifacts that we previously stole. So when we were talking about code execution with model poisoning, I mentioned in order to do this, the model files, they need to be a format which supports automatic code execution. One of those formats are pickle files, which is a PKL extension. So as a proof of concept here, I'm just going to show modifying a couple or replacing a couple of these files, specifically these model.pkl files. So to do that, like I said, there's the open source tools that I linked there. In my blog post, I have a gist with just like a small little Python code snippet that you see here. What I'm doing here is I'm creating a pickle file that whenever it would be loaded, it would run our reverse shell. And to do this, I'm actually overwriting the pickle files, these two model pickle files, from these model artifacts. Now, something stealthier would be, instead of just straight up overwriting the models, to append like a reverse shell to the model files, but I just kind of wanted to show this as a simple proof of concept. So you can see here I overwrote one of those model pickle files. I'm going to go ahead and overwrite another one, again, just to kind of show you the process. We'll actually show getting code execution in the next demo on Azure ML. And so I'm going to go ahead and, again, overwrite this other model pickle file. So we've got these model artifacts. We've overwritten the pickle files. Now what we need to do is we're going to package them back up, because again, when we downloaded the model artifacts, they were in this model.tar.gz, so we want to replace that file. So we're going to zip up these artifacts here into the same named file, and then we're going to use mlokit to overwrite those model artifacts within SageMaker. All right, so we've got this all zipped up. Just going to delete the rest of these files because I don't need them anymore. And then within mlokit, there is a poison model module that you're going to see me run, and it needs a couple of different pieces of information. We're going to give it the actual model that we want to poison. So we'll run here. So the model we want to poison, there's a poison model module. And another thing that you're going to see, a command argument here, is the source dir argument. And this is going to be the source directory on my attacker system where the my modified model artifacts are. Again, the ones that I put overwrote the pickle files. So we're going to go ahead and run the poison model module here. So this is going to figure out the model, its artifact storage location, and then it's going to upload, overwrite the correlating model artifacts, thus poisoning it. So now that the model artifacts are overwritten, when this model, this employee salary model, would be deployed in a training environment or production environment, it would run our code, which in this case is a reverse shell. And so we're going to show actually getting that reverse shell in this last demo here in a deployment endpoint, so with Azure ML. So this scenario here, how many of you heard of device code phishing? Yeah, few, yep. So we've done an Azure device code phishing attack here against a data scientist. For those not familiar, device code phishing basically allows you to get like an Azure access token as a target user that you're trying to phish. Device code authentication is like a supported authentication mechanism in Microsoft, and so we're just taking advantage of that here. So we've done a device code phishing attack against a data scientist, and we've gotten a access token as them, so we now have REST API access to the Azure ML model registry. And so what we're going to do in this demo, we're going to download a model from the registry, we're going to overwrite the model artifacts with a reverse shell code, upload that poison model, and then on the back end, we're going to be deploying that poison model to a deployment endpoint, and you're going to see our code execute and get a reverse shell on the actual deployment endpoint itself. So we're going to go ahead, we've got this, again, this Azure Access token is this data scientist. We're going to go ahead and run the check module. What this will do is it'll list any subscriptions, Azure subscriptions that you have access to. Now the reason we need that is because a Azure ML workspace or project is tied to a specific subscription ID. And so the next module we're going to do is say, hey, for these subscriptions we have access to with this credential, are there any Azure ML workspaces available? And so you can see we've got this test workspace here, and we're going to copy out a few pieces of information because we're going to need that for the subsequent commands, which includes the workspace name, the region, and then the Azure resource group that it's associated with. And what we're going to do is we're going to list any models in the Azure ML model registry that we have access to in this resource group, in this region, in this subscription. So we'll go ahead and run the list models module here. Now the most important piece of information here for the next steps is the ID field. Because whenever you download a model or you want to overwrite a model, poison a model, you do that by the model ID. It's basically the model name with a colon and then the version number. And so we're going to go ahead and download one of these models to actually poison with the download model module, and then we're going to supply the model ID here. Again, it's that ID column that you saw in the previous command. Go ahead and run this command here. All right, so go ahead and run this. It's going to, so what's MLOKit doing? I mentioned that there's a concept of these data stores in Azure ML, so I don't actually need like the SAS key or anything to get the actual artifact storage. So what it's doing is it's getting the correlating data store for that model, and then it's downloading all the files from that data store. And so we're going to note any serialized files here, serialized model files that support code execution, which in this case is a pickle file. We're going to overwrite the pickle file in this model to basically run a reverse shell. So you can see I'm just putting the path to that pickle file there, and I've got my just simple reverse shell code above there that's going to send me a bash shell on port 8888. And so what I'm going to do here is I'm going to overwrite that pickle file. Again, this is just a proof of concept. I would probably append the reverse shell instead. So we're going to go ahead and run this here. You can see the file size has changed. So there's the original model, and then there's the overwritten one that just has our reverse shell. And so now that we have this poison this modified model artifact, we're going to use MLOKit to actually poison that heart failure model. And so we're going to run the poison model module. We're going to give it the model that we want to poison, and then the source directory for the files are modified model artifacts, which again include that malicious pickle file right there. So go ahead and run this here. And so for the poison model module, it'll get that model ID we gave. It's going to figure out the data store. It's then going to take all the files in our source directory we specified, and it's going to overwrite those files in the correlating data store in Azure ML. So you can see here we've overwritten the files. And so now in the back end, what we're doing is we're deploying this model to a deployment endpoint. Again, this could be production environment, training environment, and our pickle file is going to run. And so what you're going to see here in a second is you're going to see our reverse shell come in on that Azure ML deployment endpoint. So you can see here we've got access to the actual deployment endpoint itself. So now we're going to switch gears to the defensive side. So you saw a lot of background on these training environments, the key components. You saw some different attack scenarios. Now we're going to talk from a defensive standpoint. First off, for the users that use or administer these ML training environments, really just treat them like any other sensitive user in your environment, whether it's Active Directory administrators, etc. So doing things like having a password management system for them to check out credentials to access the systems, having separate administrative accounts to access the systems, and then additionally having more monitoring controls on their systems themselves. Security awareness training, data scientists might not know why, an attacker would want to target their system. So providing some type of awareness training, catered to them on what would an attacker want from a data scientist standpoint or an ML engineer. And I think I kind of showed that today. MFA, just like for any privileged user, make sure that MFA is enabled on all their access. And then lastly, if the users are using any type of personal access tokens to access this training infrastructure, make sure their expiration dates and they're being rotated regularly. For the Jupyter Notebook environments, first off, password protect notebooks. There's an option to password protect these notebooks. That again is just another layer of defense if an attacker were to compromise, for example, a data scientist or an ML engineer. Where possible, add any type of IP address restrictions for source IPs that are valid to be able to access these environments. I've also got something listed there, limit to kernel execution times. What I mean by that is just limiting the time that the Jupyter Notebook environment will be available, especially for long-running tasks. So like if I run a reverse shell in a notebook environment, I want it to be up as long as possible. So if you can, provide some limits to the kernel execution times, and also provide, make sure that these notebook environments, they're not running in a privileged context, and how you do that is by virtual environments and running them as non-root accounts. And then lastly, making sure that users are not using clear text credentials within these notebooks, and make sure they're pulling those credentials from like an encrypted secret file or secret managers. For the cloud compute, a few different things listed there. Like most infrastructure, if you can, have an auto shutdown and auto start schedule. If a compute instance is no longer needed, then delete it. Again, this will reduce the availability of compute instances to an attacker, especially if they compromise a compute instance. If you have any unneeded services on these compute instances, disable them. So if you don't need SSH, disable it. Anything that an attacker could utilize for remote access. So like, if an attacker wanted to add, an SSH key to the compute instance so they could SSH to it over the internet, things like that, making sure that stuff's cleaned up. And then lastly, role-based access. The cloud providers, whether it's AWS, Google Cloud, Azure, they have some type of role-based identity access management functionality. So make sure you utilize that for access to these cloud compute instances. For model artifact storage and registry, similar to like, files and file shares or SharePoint, whatever, just make sure you have a process to regularly clean up and delete any artifacts that aren't needed anymore, and make sure you have access controls to access these backend storage locations. Where possible, IP address restrictions. Did it go out again? Oh, there we go. All right. And then logging and detection rules. So as part of this research, I have a number of detection rules I'm going to cover in a second related to these attacks. And then lastly, model integrity verification. So if you can, implement this control. What this does is it will detect when attempts are made to tamper with a model. And from a detection standpoint, I've got a couple GitHub repos here with some KQL queries and CloudTrail queries that you can use for threat hunting for some of these attacks that I've shown, both in my research today and also my research I released in January. So definitely check those out. Again, you can kind of use these as, as a starting point for threat hunting, and then kind of build production rules as it goes on. So for Azure ML, the detection, the KQL query I have, basically it's going to query the blob storage logs, the Azure ML logs, and it will correlate these events for any potential model poisoning. For SageMaker model theft, it's going to identify where any user identity and source IP has performed all of these actions within a 24-hour period. With model poisoning, so this is going to be where any user identity and source IP has performed any of these actions within 24 hours. And then the last one for SageMaker, so 6 different operations are used for the lifecycle configuration attack I showed. And so the query I have there in the repo will identify any user that has performed all of these within 24 hours. For MLflow, on the blog post, I've got some commands for enabling logging in MLflow, and then these are the URIs that would be used when doing something like a model theft attack that I showed. So make sure you get those logs sent to a SIM where you can correlate them for any anomalous type of behavior. All right, so wrap things up here. Make sure I want to leave 5 to 10 minutes for questions. So these, I hope after this talk, you've learned a bit and really saw how these training environments, they're quickly becoming populated with highly sensitive and business critical data, and because of that, they're going to be targeted by attackers. Last year in March, there was a blog released on kind of the first known in the wild attack against an AI, these type of systems. So it's only going to continue as more organizations are creating, developing, and deploying these models. And so as security practitioners, it's really critical that we understand these training environments so that we can protect them. Because if access to these training environments falls into the wrong hands, there could be significant impact to both the businesses and the consumers that depend on the products and services that use the models developed in these environments. So yeah, again, I've got QR code here for the blog post and the MLO kit tool. I'm on Twitter and Blue Sky. I refuse to call it X. I still call it Twitter. And then I'm also on LinkedIn. So I'll tweet the slides out, share them this week. But yeah, with that, this is my first time at Troopers, and so I just want a really big thank you to the organizers for having me. I've really had a blast. This is a great conference, and with that, I'll open it up to any questions at the time we have left.
There's already a question here.
So this is more of like an FYI that I've observed, especially with the new LLMs. Even if you have safe tensors, they'll always include a Python blob, and a lot of people just execute that. Mm-hmm. So if you think, and this is just like to everybody, if you think this infrastructure it's like 90s level security running in 2025.
Yeah, exactly, and we're seeing it more in like the environments that we're red teaming against too, more usage, and so like if I want to laterally move or privask around an environment, like maybe a few years ago I would choose some DevOps systems, and we're seeing DevOps security get a little bit better, but now with these MLOps systems, these are like DevOps 5 to 10 years ago. So
Any more questions? Okay. Then
thank you.
Thank you again.
Yep, thank you.